Alright, so for the most part, so far we've discussed gravity near the surface of the Earth, where we can just describe it as the weight being the mass times the acceleration due to gravity g. Newton recognized that it was that same force of gravity that held planets around Jupiter, excuse me, not planets, moons around Jupiter, held the planets around the Sun, and held the Moon around our own Earth, that was the force that acted between planets and even between galaxies. This is a drawing of Cavendish's original measurement to figure out what the strength of that force was, measuring g, and we'll perform a version of this later. This is a schematic from the opening to a very modern experiment to try and detect whether or not gravity continues to go like 1 over r squared at very small length scales, down below the millimeter scale. It's very hard to detect gravity at such small scales because it is so very weak. It's a very weak force compared to the other ones at small scales. Alright, so what we learn is that gravity, the force of gravity between two arbitrary objects of mass m, 2-point particles, is proportional to the mass of the two particles multiplied together, m1 times m2, inversely proportional to the distance between them squared. Our hat tells us it's along the line joining them. The negative sign tells us that it's attractive, and this capital G is a constant that makes the units right and tells us just how strong that force is in standard units. It's actually a very small constant. We will be measuring it later, but it turns out to be about 6.67 times 10 to the negative 11, and the units are newtons meters squared per kilogram squared. So it's a very small constant. If we have several objects acting at once, several objects gravitating at once, then we simply add up the individual forces of gravity. Okay. Add up the force of gravity from each individual object on the object we're considering. So if we're looking for the force on object 1, we add up the force from object 2, object 3, anything else, and add them together as vectors. Add together the force from object 2, object 3, so this is the force from 2, this is the object 3. We add them as vectors to get the net force. If we're talking about the force of gravity from an extended object, we change that sum into an integral. We probably won't do a lot of extended objects except for spherical objects. In the case of a spherical object, if you're outside of the object, then we can just treat it as if all the mass was at the center of the object. Okay? So for example, when we talk about you and me near the surface of the Earth, we're not really at any distance away from the Earth.